sklearnmetricsRocCurveDisplay. Description: the RocCurveDisplay class in scikit-learn provides a convenient way to visualize the receiver operating characteristic ROC curve, which is a fundamental tool for evaluating binary classifiers. Inputs: y true. This is the true label vector, representing the actual class labels for the data points. It should be a 1D array of binary values 0 or 1 or string labels. Y score: this is the predicted probability or score vector output by the binary classifier. It should be a 1D array with the same length as y true. Estimator: this is an optional input that represents a fitted binary classifier model. If provided, the estimator predictProba method is used to obtain the predicted probabilities for the given input. Data Ax: this is an optional input that allows you to specify an existing matplotlib axis object where the ROC curve will be plotted. Outputs: RocCurveDisplay: this is the main output of the RocCurveDisplay class. It represents the visualized ROC curve plotted on a matplotlib axis object. Ax: this is an optional output that represents the axis object on which the ROC curve is plotted. If no ax input is provided, a new axis object is created. Steps: calculate true positive rate TPR and false positive rate FPR for different threshold values. Plot the TPR against the FPR on a graph. Optionally, add labels, legends, and other plot annotations to enhance visualization. Metrics: area under the curve AUC: a common metric that quantifies the overall performance of a binary classifier. Higher AUC values indicate better model performance. Precision: the proportion of correctly predicted positive samples out of all samples predicted as positive. Recall the proportion of correctly predicted positive samples out of all actual positive samples. Visualization plots: RocCurve: a graphical representation of the classifier's performance at different threshold values. The curve plots TPR on the y-axis and FPR on the x-axis. AUC score: the area under the ROC curve is often calculated and displayed as a numerical value. Fine-tune parameters: posLabel specifies the label that should be considered as the positive class in the binary classification. This allows you to control how the TPR and FPR are calculated. Name allows you to provide a custom label for the ROC curve that will be used in the legend. Estimator name provides a custom name for the classifier used to generate the ROC curve, also used in the legend. Drop intermediate: this parameter controls whether to drop intermediate points on the ROC curve that are not strictly necessary for plotting. Color defines the color of the ROC curve line. Line style specifies the line style for the ROC curve. Line width sets the width of the ROC curve line. Uncertainty methods: confidence intervals using techniques like bootstrapping. You can estimate confidence intervals for the ROC curve, indicating the uncertainty in the estimated curve. Calibration curves: these curves show how well the predicted probabilities align with the observed probabilities, providing insight into the reliability of the classifier's predictions. Challenges and fixes. Challenge 1: overfitting to the training data. Sample use case: a classifier trained on a small and biased dataset may achieve a high AUC on pay training data but perform poorly on unseen data. Fixes: use cross-validation techniques to evaluate the model's performance on multiple folds of the data. Reducing overfitting. Employ regularization methods, such as L1 or L2 regularization, to penalize complex models and prevent overfitting. Challenge 2: imbalanced datasets. Sample use case: if one class has significantly more samples than the other, The classifier may be biased towards the majority class, leading to poor performance on the minority class. Fixes: use resampling techniques, like oversampling the minority class or undersampling the majority class. To balance the dataset, employ cost-sensitive learning techniques that assign higher costs to misclassifications of K. Minority class, encouraging the model to focus on its accurate prediction. Challenge 3: choosing the optimal threshold. Sample use case. While the AUC provides an overall measure of performance, choosing the optimal threshold for a specific application requires considering the relative importance of precision and recall. Fixes: use metrics like F1 score, which balances precision and recall, to evaluate performance at different thresholds. Consider the specific requirements of the application, such as minimizing false positives or maximizing true positives, to determine the most appropriate threshold.